Testing. Everybody hear me okay? Hey. Thanks for joining me just before lunch. Hopefully I will make you hungry for some bit of food. What I want to talk about is lots of different world representations in games, but I want to start with a story. Once upon a time, we had no word for blue. I don't know if anybody already knows this, but in the Iliad and the Odyssey, Homer described the sea as wine dark. And we've actually got the idea of that the colors that we have in our language have built up over time. Dark and light to start off with, all the way through to colors that only my wife knows and I haven't a clue about. And it made me think of my experience with Prince of Persia. And it seems to have a similar trajectory from monochrome through CGA, EGA, VGA. But really, what I'm interested in is the fact that when I first played it on my Amstrad PC 1512 in CGA, the gameplay was pretty much the same as the 2007 version of Prince of Persia as well. So while there was more colors, which was better graphics, and it's still the same gameplay, does that mean that the graphics isn't necessarily the gameplay? Now, I probably am wearing my rose-tinted specky glasses here, but that's okay. But there must be some other part of the world, or the game world, that we're not necessarily seeing. Now, Prince of Persia has evolved as well, so it's not just the color language that's evolved, it's the gameplay elements and the graphics elements. So we've obviously had The Lost Crown last year, and I believe this is coming out this year as another version of Prince of Persia. Arguably, it's a Prince of Persia skin on a different game. But it's still, you can obviously see how gameplay has developed and graphics has developed, but they're not necessarily synonymous. Now, whenever people first broke light apart in a prism and did a bit of an experiment to get temperature, somebody accidentally left a thermometer to the left of the red section of the light spectrum. And that was the thermometer that actually ended up getting most energy hitting on it. So there was something happening that we couldn't see back then. At the other end of the spectrum, ginger Irish fella goes out in the sun, gets burnt. That's the UV end of the spectrum. We're seeing visible light, but we're feeling infrared, and I'm getting the effects of ultraviolet. Now, there are other animals out there, like the gloriously colored chicken, that can see in ultraviolet spectrum, but it still goes to the point that we're seeing some stuff and feeling other stuff within our own senses. And of course, graphics is mostly about sight, one of those 5 main senses we're talking about. Sight, sound, taste, touch, smell. But there's also other senses that we don't immediately think about, and that's, I think, actually where the real gameplay is. Those intrinsic internal senses, sense of achievement maybe. But there's other senses like I'm starting to feel hungry, yeah, lunch is coming on. Body awareness, useful for maybe our VR games. Sense of balance, also very useful for our VR games. I've fallen over plenty of times. And our sense of time and our loss of time and things like that. All of these are ways to perceive and interact with the real world, but it's actually the same thing that we're interacting with any world, including our game worlds. Now, if we take those in sort of intrinsic senses, the taste, touch, all of these can be looked at in terms of inputs and outputs into our game. Obviously, we're outputting graphics so people can see it. To a certain extent nowadays with facial capture, eye tracking, there's some input potentially into the game. Same with audio. I can talk into my microphone, I can blow into the microphone, there's various interactions there, and obviously we get our audio out. I don't want to know about the games that are doing with smell and taste, unless taste is just putting your game cartridge in your mouth to see how that tastes. And then obviously haptics comes into play with touch as well. Dual controllers, circle, strafing, wife hasn't a clue about, she knows all the colors. Circle strafing is a whole other language that she doesn't know about. But touch is obviously very important, input and output. And within the game systems, 3 of those senses at least correlate directly: graphics, audio, and haptics. Other senses that I'm obviously going to be biased about, coming from Havok, is the physics representation of the world and the navigation representation of the world. Now, I do want to start off by setting expectations. I'm not an artist, as is clearly evident. My focus here is really to highlight the different other representations of the world that aren't graphics. but also see how we could, better graphics in games has meant more expensive creating all of those, that's richer, more beautiful worlds, but we don't want to incur that cost on generating the physics representation and generating the navigation representation. We want to be able to see if we can automatically generate those. And then also we'll sort of touch on a couple of little issues about how all of these systems interact and the problems there and how some of the tools engineers can resolve that so game developers can focus on developing the game. I'm also going to look at things in two different ways. Design time, in Unity it's called authoring state rather than runtime. But here I want to be able to highlight the fact that from the graphics we can generate the physics representation of the world. From the physics representation of the world we can generate the navigation representation of the world. And hopefully that can be as automatic as possible without, again, incurring cost. Now I've shown this before, but here's a little bit of an example where we can see the simulation happening inside Unity. And obviously there's physics. Gravity is pulling these objects towards the planet. There's something wrong here that we can't quite see. That doesn't look quite right. Okay? Can anybody guess what's going on at a design time? Yeah. Now, this is obviously immediately obvious if you're happy enough with physics. But if you're not, then you want to be able to have debug tools that can highlight the problem straight away. And one of those is the Havok Visual Debugger. I'm emphasizing the word visual because we don't want the physics nerd to be the only person to be able to debug these sort of problems. So this is our Havok Visual Debugger connected up with Unity. And once you're connected, you can see all the spheres that are the asteroids. And then whenever I move my camera out of the way, now this is hooked up over a network, so it can be directly hooked into the game. All you're doing is serving information to the visual debugger, and then when you zoom out, you can immediately see, quite right, that planet is a cube rather than a sphere. But by visually seeing that, anybody in the development team could immediately go, oh, I've gone and set something wrong. There's also the fact that there's an error between the graphics representation and the physics representation, so this maybe could be highlighted automatically. And now when we flick on the sphere instead of the box, then it collides as you'd expect, and everything now correlates together. So yes, there was runtime elements in that, but it's really a design time part where I'm setting my physics representation on a particular object. So it's not clear lines, but hopefully you can understand that I wanted to focus on the runtime, authoring side at that point. It's a very different pattern whenever we're looking at the runtime. Each of these systems are providing information to all the other systems. Have I got every link together? So the physics rigid body transforms are telling the graphical representation where to draw. The navigation system is saying what sort of velocity can my character run at in a particular direction. Now I'm focusing on graphics and physics and navigation. Of course, audio's in there as well and all the other subsystems. This is just a nerdy example of how you can extract the physics information used to trigger sounds. This is a visual version of that sort of scenario inside our Havok SDK demo set, which is definitely programmer art because there's no sound whatsoever and we're just slapping up things. But even here, the amount of information that we can get from really rich simulations doesn't lend to being a sort of simple approach of I'll do some work on a callback. We have to think that the simulations that we're dealing with are much more advanced, much more detailed, so we can't just process every single collision one at a time through on-collision callback, for example. This is a whole separate data stream that we can provide to people to optimize in parallel what they want to do with a sort of number of events that are happening at real time. There's also the fact that this might be a little bit difficult to see, but I'll just sort of talk over it. There's also the fact that at design time, we might parent child objects together to make it easy. I want to be able to drag a ragdoll around, for example, from the pelvis. But at runtime then, even if there's a hierarchy on the graphical side of things, the physics drops that hierarchy altogether. Every single rigid body becomes something on the root level. just for performance reasons. We don't want to have to deal with handling all those parent-child relationships in the transform just to do a physics simulation. But it also means that the design time hierarchy and the runtime hierarchy are effectively two different things. This is all happening behind the scenes, but we're starting to have to worry about that. We have to have optimal runtime representations, and we have to have design time representations that are appropriate. So there's even a mismatch between those two sections. And the data, how the data is laid out is different. So this is just, again, apologies if you can't read it, but this is two versions, the design time on the left with a hierarchy and the runtime on the right where the hierarchy is being flattened. And the data and how it's arranged in memory is very different in both cases as well. So really what we've got is a distinction between authoring, design time, and runtime, and then we've got our three systems, and how those systems interact with each other is very different. I'm going to look at sort of examples of each of those within the context of looking at characters, maybe looking at just random dynamic objects, and also then looking at the environment as well. So if we talk about characters, I love this game. I loved it because the graphics representation and the physics representation were already correlated. I didn't really have to worry about it. It was great. That's not the case in most scenarios. So while my skinned character there is what I'm looking at, behind the scenes there's actually potentially a lot of stuff going on. Let's break that apart a little bit. Again, my artist skills are on show. There might be a cloth simulation on top of the skinned mesh. We've obviously got a high-resolution skeleton driving the skin mesh, animation tracks that are driving that skeleton, a character proxy. Capsules are normal, but it could be pencil shapes, it could be any arbitrary shape. Then I've got our ragdoll, which is a lower resolution than our animation skeleton. And then we might have a navigation agent view of the character as well, which is maybe just a character height and a character radius and some path it's following. So we've talked about each of those parts, but they all fall into one of those systems, graphics and physics and navigation. Cloth's an interesting one. It might fall into both, but we can't have perfect delineation. So the character at design time, at the minute, it's all setting the character up in each system independently. There isn't any connection between the graphics and the physics and the navigation. Every time I have to go in and set my character height in all three systems. So it's kind of like a manual process. Here's an example where I've manually created a graphical representation, and I've manually created a physical representation, obviously to highlight the problems of them not being correlated. But this is a manual process. I've set up all of the objects. I'm handling all the bookkeeping. That's such a pain in the butt. At the very least, we should be able to take our skinned character, select some skeleton bones, and then use the bone weights in order to generate the physical representation, and then simply be able to toggle what sort of physical representation we want. But even there, that's not good enough. We really want to be able to take the graphics. There's the example of the skin mesh and the bone weights and a subset of bones to generate the physics rigid bodies. But why couldn't I take all of the bones that I'm interested in and the animation tracks and automatically set up all the constraints with the limits in those constraints? And why couldn't I take all the ragdoll parts and automatically set up the character proxy size? And why couldn't I take the character proxy and automatically set up the character height in the navigation system? We're not doing that yet. That's to a certain extent on us if we're developing our engines or developing middleware, but it's a direction that we really need to go. And then the character at runtime, obviously the skeletal animation is updating the skin meshes, but the velocity coming from the navigation system might be informing the animation root node where it should be and what speed it should be moving at so that you could blend animations together, or the character proxy on the physics side might dictate that the character can't move in a particular direction or can't jump in a particular height. So all of these systems interplay, and the question then is who's in charge? If you've got an animation-driven character, your artists are going to be happy and it's going to look nice, but it may well be off the nav mesh, it might fall off the world because it's just following what the animation's doing. If you've got a physics-driven character, it's going to be in a safe location, that's okay. It's going to have foot skating all over the place, and your artists are going to be disappointed because that blend is going to look terrible. And if it's a navigation-driven character, then it might locally be safe because it's moving from one frame to the next. but it's a short-term thinking on that path that it's following. It's only from one frame to the next. But there are other things that we can do as well by adding in further information. Say, let the navigation character look ahead for a good number of frames into the future. And that allows maybe the animation to have more information to select a better animation because there's a smoother path and smoother transitions. So again, at the minute all of these systems are separate, we're going to have to think about how we can bring them together in a little bit more coherent way. If I think about objects, yes, objects are looking lovely. But by default, the physical representation doesn't necessarily match. This is slightly different from the planet being a cube type scenario. This is, for the cheapest physics simulation, you're just going to use a convex hull. But it also means that the bottles and the plates don't fall through the bookshelves, they don't fall through the scopes on the wagon wheel, the tables don't interact together. Now, there are tools to automatically decompose the physical, or create the physics object based on some error level. And that's quite a nice, simple, single heuristic. Given this error margin, give me the physics representation. And then we can have a physics representation that correlates nicely with the graphics representation. And there are similar things on the navigation side of things. A large object might fall on a nav mesh and cut a section of the nav mesh so NPCs can't fall through there. But that should be automatic as well. So we have the possibility of going from graphics through physics into navigation representation. So we could be taking our really nice graphics representation and with this error margin generating the sort of a compound convex representation of the physics at different levels. Even if the geometry that we're taking in from the graphics isn't perfect from a physics point of view, or it's photogrammetry or something's rushed, we can still generate that. And then on the navigation side of things, here our physical objects are cutting the nav mesh. And in this example, it's quite a clean, close, low error. But here we're actually just using maybe more of an OBB of the physics to generate the nav mesh update. So we can have systems in place to automatically generate these things, but we have to consider the performance cost of having all these systems work together. Now, some of our customers, especially if they're doing their own engine, can set up physics LODs as well. So we do have a notion of an LOD shape on our rigid bodies. So we can have a mesh shape for queries. If we're doing ray casts and we want to shoot the car and find out exactly where on the mesh it is. I think in Unreal there's an example of a simple and complex collision, and you can set simple as complex or complicated. With Havok, because it's a middleware technology, it's a little bit more adaptable under the hood, but then it's exposing that adaptability at the design level. And this seems to be a fairly coherent structure that people are setting up to get the maximum possibilities with the minimum number of combinations in setup on our pipeline. So mesh for queries, a convex hull, or maybe a compound for general collisions, and then maybe even a low-level single primitive like a sphere for cheap collisions. So just an example of that, again, this is in our SDK rather than in Unreal or Unity. The cubes are falling down and colliding with the convex hull. The ray cast is hitting the mesh. So you can see sometimes the ray doesn't hit anything because it's going through the gaps in the mesh. But again, we're leading into runtime. So again, even taking a lot of rigid bodies, taking all their transforms and applying that to the graphical representation, that in and of itself can be a costly endeavor. It is something that we're looking at to improve. But this is runtime decisions that we want to enable. So at runtime, there might be some game logic that decides that this teapot will collide with the ground as a mesh, or it collides with the ground as a convex hull. But it's getting gameplay logic and being able to use that to drive your setup through different heuristics that are important at runtime. So you can set up everything once in design time, and then at runtime have different logic to get different performance behaviors. This is another example of a runtime decision. size in this particular case. So the big object is going, is this playing? Yeah. The big object is going to fall down, and on the landscape, it's the single convex hull that the large object is colliding with the landscape, but the small objects can collide with a more detailed representation of the big object. Alternatively, it could be speed. As things are moving fast, we use the crude representation, and then when they slow down enough after the initial collision, then we can switch to a different representation as well. Now again, there are setup and bookkeeping needs that we want to remove, so you don't have to worry about this thing. And then at runtime, all you need to do is set my velocity threshold, or set my size threshold, or set my platform. If I'm on Android or Switch, I might have simpler representations the whole time versus PS5 or Xbox, where I can do a bigger detail representation. Another example here is, it's a different use case. Depending on which objects are hitting, the chairs, when they hit other chairs, are using the more detailed representation, but when the chair hits the landscape, it's just using the convex hull. There's absolutely no need to be doing a detailed collision with that chair on the ground, for example. Now, we've talked about lots of richer ways of doing the physics representation. Graphics, we've got lots of tools for identifying bottlenecks there, but we do have to update our visual debugger to be able to handle these more interesting representations of the world, find out individual collisions between subparts, find out exactly which shapes are colliding with any particular other shape. So we're actually having to advance our visual debugging tool in order to provide more information, but also allow your own team to wrap that up and highlight things based on your game logic, and I'll touch that a little bit later. There's also the fact that these objects are being put together. So if I just set up this scaffolding scenario inside, say, a fracture pattern or a geometry collection in Unreal, of course I can smash it and things fall down and it looks lovely, but it doesn't feel right. So there's a runtime element to that physics as well. We don't want you, in the same way as with a character, you don't want to have to go in and manually set all of those constraints for any particular ragdoll piece. We want you to be able to set a very simple, this is wood, these are overlapping a little bit, here's how much I want them to bend before they break, so that at runtime the behavior you get from the physics is also much better, without the cost of having to go through every single strut and set all of those constraint information up yourself. Just again, I've been focusing on physics here, but on the navigation side, we saw how the rigid body representation can update the navigation, but we can also paint into the navigation space. So rather than cutting holes in the navigation, you could paint an area in there, so the character could pass through it, but there might be a cost associated with it. And also, even in the bottom right here, you don't even need to update the nav mesh to have velocity information coming from the physics to tell a navigation agent that it should avoid the spinning blades. There's information from those rigid bodies that are being keyframed, and that can be passed directly to the local avoidance model for the navigation representation. I'm totally only skimming on a lot of this stuff. Hopefully it's representative of some of the issues you've maybe seen, and I'm totally up for chatting afterwards about more specific examples, but I want to just touch on these three areas. So, in terms of the environment, again, this is a really simple, crude example. If we're only looking at the graphical world, we've got some bodies in the scene, and we've got a start point and an end point, and this is just a sort of debug functionality to show the path. Now, it mostly makes sense what's going on with that path. It's trying to avoid the moving objects, it has to go around to the left, or it has to go around to the right. But sometimes it bounces all the way around the top right. And sometimes there's a weird kink in the bottom. And if it's just the graphical representation, you haven't a clue what's going on there. So, of course, in the engine, you can put all of these things up, but here's our visual debugger again. We've got the notion of different viewers. You can enable the physics shape viewer, you can enable a nav mesh viewer, and immediately you can see, oh, that top purple guy is having his effect on the navigation world changed every now and again. That's why the path goes around the very top sometimes. That yellow guy, who's a dynamic object, he's got a crazy big area that he's affecting the nav mesh. Why? But that's what was causing that weird kink at the bottom of the path. Again, if you're only looking at the behavior from the graphical side of things, you won't know what's going on with this holistic sort of environment view here. Okay, now sometimes you might want to do that. That's okay if you want to do that, but sometimes you don't, and a lot of times you don't. Okay, so again, how do we move from our lovely graphics, from the environment side of things, into the physics representation and into the navigation representation? So this is just an example of a demo we set up. We were testing nanite at the time and what was involved in dealing with a physical representation of nanite. But we can get the crudest representation from the nanite geometry, and we can use that then to generate the physics representation. Of course, Unreal's doing that anyway, but there's other things that are going on in this particular demo that I don't like. This is the overall scene. If we look at it just from the physics perspective, every red box is an ABB, sort of the crudest level of the physics representation. So I can immediately tell there's a lot of individual pieces in this world. So every frame then, every single individual physics object is then having to update its transform. We might not want to have to do that. So we actually do have functionality in Havok to be able to take those kit bashed levels and generate a single, simpler representation of the world that's much more optimal for the physics. So rather than having 50,000 individual bodies, you've now got one, and it's a mesh, and all the internal phases are gone, so therefore it's saving memory as well. Pros and cons, there always is, but you know, we're having to do a lot of things behind the scenes that aren't just about lots of rocks falling down and going boom. Speaking of lots of rocks falling down going boom, this is again a graphical representation. I'm running through the scene. I didn't want to risk loading this project up and actually doing it live, but I could if you hold me to a candle. But obviously we're blowing things up. We're using geometry collections in order to handle that level of simulation, because individual actors being updated from every individual rigid bodies is a killer in terms of performance, but there are ramifications for how we've integrated with that. Here's our visual debugger connected with Unreal as well. We can see our purple character controller as our capsule. We've got little sort of trigger volumes in front where our arms are. But you can immediately see that the physics representation is a little bit different from the graphical representation. You can see the lovely bits of level of detail happening when the objects get broke. But there's also a couple of weird things. Maybe you can't see, but there's these circular things which I can definitely see through. But actually, if I see it here, for some reason, I wouldn't be able to run through them. And I don't know why. It's maybe a little bit tricky to see. There's also the fact that if I scrub back a little bit, the ground here is pretty crude in terms of the physics representation. And then the steps are actually convex hulls for the steps. So they're not even simplified versions of the geometry. They're actually convex hulls so that the character controller can more smoothly pass over the top of that geometry. There's also, if I scrub back a little bit further, there's different levels of detail. Like this area here, actually, yes, there's no point in putting my mouse on my screen. This area here is quite detailed, but you know, there's other areas that are quite smooth. That actually turned out to be the artists had a lovely little particle effect, and they wanted those wall bits to have the sparks jumping in more detail. But if that's an artist decision, then just for sparks, and then you want your character to smoothly slide along, there's other potential conflicts in place as well. Sorry, I was talking about where's my mouse? I was talking about a section and pointing on my screen, so you can see. This round, I did it again. Where's the mouse? Everybody, there we go. These round things here, you can obviously see through them, but they are over here and you can't. So until I showed this to the artists, they hadn't a clue that that was going on in the physics. So having this separate standalone tool just makes it really easy. Hook it in and grab some recordings. Now that's the physics representation. We didn't really have navigation on this demo, but we created some nav mesh. But the main point here is that there's a ton of data being generated for the nav mesh automatically. We should be setting up seed points. We should automatically be recognizing where the character moves, so we don't bother generating nav meshes for other parts. So that, again, that's where potentially character information could come into play. But you can also see just where the steps are. If I scroll back, it's a much simpler representation again, even from the physics. And of course, there's no wall information in the nav mesh. One interesting thing we did find, and maybe it's unique to our approach for navigation representation generation. Ooh, that was amazing that I said that. It's good on it. I can't remember what I said. Height fields are obviously a regular point of representing the surface. If we just simply generated a triangle mesh from those heights and pass that into our navigation representation, it's a nightmare for performance. But what we did find then was we created a tessellator for the height field. Tessellate it, stick it into the nav mesh generation, orders of magnitude faster in terms of design time. Again, it might be our navigation representation that was, and the way we handle things that was an issue with. But this was something that was unique. But it also now means that we have to think about a tessellation toolkit. Hopefully, we can hide it from the artist, and all you do is, what's your error margin between the physics and the graphics and the navigation? But we have to then think about geometry tools that preserve boundaries between materials and maybe add in extra functionality where, depending on how high up the mountain are, maybe it's cruder tessellation because the character's never going to get up there because the red area is somewhere that it can't walk, etc. So we do have tessellation functionality, and it's stuff you don't really think about whenever you're thinking about physics or navigation. It's here's an asset generation pipeline and all the issues about generating those assets and making sure those assets are clean, making sure when you create a convex decomposition of a tabletop, the top of it is flat, the bottom of the box is flat. The windows, whenever you do a convex decomposition of a building, stay windows and they don't get filled in. There's a bunch of stuff that we could be automating more so that you don't have to be manually processing this. Or even if we don't automate it, at least we can say, what's your error margin? Here's the points in your assets that we've created in different representations that you might want to look at and highlight them. So this is just another example from the SDK where we are preserving all the material boundaries while we tessellate this thing in real time. There's another part in the navigation representation that we can provide. We call it traversal analysis. So there's a step down, but I can imagine if there was a table there, I could vault over it. Or if there was a gap, I could jump that gap. Or if there's a wall, I could jump down off a balcony or vault over a fence. And we provide automatic markup for all of those scenarios. Ducking under something, jumping over something, vaulting over something. We also have to provide more visual information to debug that scenario as well. Most of the time it should work fine. You set your parameters, I can vault over this wall. But we're providing richer tools to debug each step of this generation pipeline. Here is the top height that I'm going to allow my vaulting over. Here is the boundary structure that I'm going to try and look for geometry. Here is the sort of information that I can gather whenever I request information from the geometry. And all of those pieces you can now debug and find out exactly what's happening in each step. At the end of the day then, you have a clean representation of a surface that then the animation system could do hand planting and stuff on. But most of the time, the visual debugging functionality, currently if you grab one of the tools, will go, here's the data at the end of that frame. Here's the data at the end of the next frame. It's up to you to be an expert and know how did you get from one frame to the other. We're having to now look at all of the individual steps in asset generation and all of the individual steps in iterative algorithms as well at runtime. So the environment at runtime, we're obviously, again, interacting on the navigation physics. Here is the same scenario, but now there's a dynamic object blocking that world view. I can't get up the path anymore. To a certain extent, we've already seen this. So the object is blocking the path. That's the physics representation. But again, I can turn on different viewers. So I can see I can turn off the physics, turn on the silhouette generators, as we call them, that cut into the nav mesh, turn off the physics. And hopefully, it's possible to see that big boulder is cutting a section out of the path. Okay, so that's okay for an individual actor. It's easy to set up a silhouette generator. But what about that use case where we had the arch Right now, unfortunately, physics, fine, we'll handle all of that. And it falls down nicely, and it blocks that pass from a physical point of view. And obviously, the graphics is being updated, and there's that hierarchical fracture going on, which is quite nice. But if we play this in the navigation representation, this is a really exciting bit of the video, because we can see what happens to the dynamic scenario in the navigation, and nothing happens, because we haven't automated that part of the pipeline. You could recognize the fracture event, find the size of the object, add a silhouette component on it, and then have it fall down and cut that. I don't want you guys to have to do that. It's on our bug tracker, but that's the sort of example of, we've got it working at one level, gameplay is pushing out towards these levels. We need to take away the bookkeeping code so that you don't have to do it. This is another example that highlights a few issues. This is a sort of a Lemmings type demo in our game engine, or in our demo framework. You can turn on the navigation viewer, but if I'm just displaying the navigation representation on top of the graphics, then Z fighting and all that other good stuff. So even something as simple as being able to offset the view. Whenever I want to then put the physics in, I can start dropping in bodies. Let me just move forward a little bit. I can start having objects fall in, and again, we can see that it's cutting the navigation mesh. But there's also these other parameters. Whenever we're doing a big explosion, there's lots of work being done by the physics system, and it costs lots to update the nav mesh. We don't want it to happen at the same time. So we can put thresholds around our objects so that if it moves a little bit, I don't bother cutting. So that's an optimization we can do. So that if it's something that's swaying, then there's no point in cutting the nav mesh. Just make it slightly bigger, and we'll avoid it around the place. So there's a distance threshold you can put on. You can also put on a velocity threshold. There's no point in cutting the nav mesh if your object's moving fast. So we have to consider we're updating the navigation representation, and we're running a physics representation. The explosion happens, everything settles down, deactivates, then we can do the work of updating the navigation representation. So at runtime, we're balancing the load to get the most out of our simulation. And all of these things have to be considered as well. Okay. This is just another example of how we're having to provide more tools to do debugging. This is our first programmer level version. We're going to have fancier versions that are maybe guided for anybody in the team to be able to handle it. But here, it isn't one frame to the next. It's every iteration of our A* search that we're now debugging. So you can clearly see the cost of that path. Now, if somebody comes in and says, there's a weird path, why is it going all around the top? If you're just following the character, you haven't a clue. But because we can now debug every single internal step, we can see that there's a particular edge that has been marked as non-traversable. I can immediately then go and find that in the graphics, and maybe there's an asset, same as the cube on the planet. But then as the algorithm continues, why is it not still going around the bottom? And it turns out that there's facial costing information on some of those faces as well. So it can't go that way, and it can't go down now. So we immediately see, because we can check every single iteration of the logic for this particular search, that's the natural path that it has to take. But if you were just looking at it from that character's walking around there, you're never going to see that. And we're wanting to provide this sort of advanced version of our visual debugger so that you can mark up your own algorithms as well, your own iterative character logic, for example. Anyway, come to a conclusion. I've talked about things like visual debugger. We've got terms like welding and particle. These are overloaded terms, and we really need to improve our shared lexicon. So is it design time or is it authoring time? So we can have a common parlance. I don't think anybody would agree on what a game is, for example. But on those extrinsic things that I'm talking about, the description of the world, the querying of the world, the tech providers, us at Havok, the engine developers, we can be providing a better design time pipeline, so you don't have to worry about generating things manually or bookkeeping things manually in the runtime. So we'll provide more connections between systems, and providing more tools so that you can find out the problems between all of these systems when you need to. But ultimately the aim is so that you guys can bring the fields, that the game developers should be developing the gameplay, not necessarily having to generate all of these different representations and do all the bookkeeping for all these representations. We want to do that. I'm going to end on this. This was my first purchase of a game, a box set with a 5¼ inch floppy for my Amstrad 1512 of Speedball. Worst experience of my life. I did stay at the start, the Prince of Persia. It didn't really matter. CGA version of Prince of Persia played just as well. It was beautiful. Playing Speedball on a big analog joystick on a PC 1512 was terrible. But hopefully, I mean, I did that deliberately at the start. The word blue wasn't in blue. This was grating some artist somewhere and some font designer. But hopefully, obviously, we want to be able to bring all of these representations together and have game developers focus on developing gameplay. Okay, that's me. Thank you very much.